You might have noticed, if you've ever pushed a heavy box across the surface, that it's very hard to push that box, to get that box moving. But once it's moving, it's actually a lot easier to keep it moving. What causes these things to happen? First of all, what prevents the box from moving at all? And the answer is friction, right? That's our topic for today, and how to do some of the calculations around friction. So friction prevents it from happening, or prevents that box from moving very easily, right? And the heavier the box is, do you think that it's going to be easier or harder to push? Probably harder, right? If you have a really heavy box, it's going to be harder to push, so there's probably more friction involved. So in the scenario that we just talked about of you pushing this box across the floor, there are actually two types of friction involved. The first type of friction is called static friction. And static friction occurs when you're trying to get that box moving, when the box is static. So when the box is still, we have the force of static friction preventing that box from moving. So I'm just going to draw a quick free body diagram here. Here's our box. When we're trying to get that box moving, I'll put here, this is the force applied. There's a force of friction. I'm going to put it down here. And we'll call this Fs for static friction. And that's the force that basically keeps the box where it is when it's still. Once, though, you get that box moving across the floor, it overcomes that static friction. Sort of once that static friction has been overcome, it starts moving across the floor. And then we get this sliding, this easier sliding. There is still a friction force involved, but we actually have a different name for that, and that is kinetic friction. So now we actually are able to apply a smaller force. If this force is bigger, sorry, let me just do them to scale. We'll call this a nice big force here, and we'll call this force down here, and we'll draw it as a nice small little force here. You need less of a force applied, and the force of Fk for kinetic friction is going to be smaller than that static friction. This is called kinetic friction. So this is generally how this behaves, how objects behave when we slide them, or when there's friction involved. When they're still, you have to overcome this static friction to get them moving. Once it's moving, you actually have to apply less of a force to keep it moving because we are dealing with kinetic friction. We're going to talk about in class what actually causes these two different types of friction between the two surfaces. That's something we'll talk about in class. For today, or for this video, we're just going to talk about how to calculate these two different types of friction. So again, we talked about before how the and you can fill out the answer to question 1 in your own words there, the difference between static and kinetic friction. The next thing to keep in mind is we said the heavier the box is, the harder it's going to be to push. And that's not necessarily because the box has more inertia, which we know it does, but there's actually more friction involved. And the reason for that is because, well, if we think about this box, we're not actually done with the free body diagram here, right? We actually have a force of gravity, and going up we have a normal force, right? And same thing for this box. We have a normal force and a force of gravity. And the more the box presses on the ground, basically between this surface, right, the surface and the ground, the more friction there's going to be. So essentially what it is, the more normal force an object or the surface has to exert on the object, the higher the friction force is going to be. So to show this is a mathematical relationship, we have this, that the force of friction, let me switch to blue, yep, the force of friction is equal to some value times the normal force. Both of these are vectors, they're forces, right? So let's look at what this equation means to us. It basically tells us the force of friction is dependent on what the normal force is. If the normal force is higher, the friction force is going to be higher. So they're directly proportional to each other. But we have this weird symbol here. And what it is, that's called a mu, mu. It's a Greek letter. It's another Greek letter. And it sort of looks like a U with a tail on the front, right? That's basically what the symbol is. And we call that the coefficient of friction. This should obviously coefficient of friction in that question too there. Right? So it's the coefficient of friction. And if you think about it as in this equation, you can think about it as how much of the normal force gets converted to friction. You can think of it almost as a percentage. So, for example, if the coefficient of friction is 50%, that means the friction force is going to be 50% of the normal force. Or if it was 75%, the friction force is just going to be 75% of the normal force. This coefficient of friction depends on the material you're dealing with. So if you actually go back to the back of this package that you have, it lists a bunch of coefficients of friction. Notice also there is a separate coefficient for static friction and kinetic friction. So depending on whether the object is stationary or moving, it's going to be different. But these are all decimals because, again, it's like, so for example, wood on dry snow, 22% of the normal force gets converted into friction force. Or if the object is already moving, 18% of it gets converted to friction force. So this is a very convenient way to basically calculate, or approximate, I should say, a friction force acting on an object. As long as we know the normal force or the weight of that object, we can usually figure out the normal force. So just to clarify, we have two different mu values, mu k, and this is for kinetic friction, and that's called the kinetic friction coefficient. And we have mu s for the static friction coefficient. Coefficient. Okay. So we're going to skip the rest of these questions here. We're going to discuss a lot of these in class. So let's skip straight to the calculations and see how we can apply these things. So we're going to skip to question 2 on the next page. 75 kilogram hockey player glides across the ice on his skates with steel blades. What is the magnitude of friction acting on the skater? So the first thing we should always do is draw a free body diagram. We know the hockey player is 75 kilograms, so what forces can we find? Well, we know there's going to be a force of gravity, and we can easily calculate that just by doing 75 times 9.81, which gives us 736. I'm going to round to 3 significant figures, just take an extra one just to ensure no rounding error. And that also means it has a normal force of 736 newtons. So our normal force and our gravitational force in this case are the same. Are there any other forces? Well, it doesn't say so in the question. They're just gliding across the ice. And if they're gliding across the ice, there's no external forces pushing them forwards or backwards. They're just sort of moving along. And then friction is the only force that's applied on them. And that actually is the third one, which we should include. So if we assume the hockey player is moving in this direction, so I'm just going to put a V there to represent that they're moving in that direction, we can assume the friction force is going to be in that direction. So F of F for friction. And the other question to ask ourselves, is this static or kinetic friction? Well, you can ask yourself, are the surfaces moving over each other or are they stationary? And because it says glides across the ice, we can assume that this is actually kinetic. It's moving, right? So I can actually replace that with not just FF for force of friction, but FK for kinetic friction. So our equation to find kinetic friction, well, we have a general one, right? Like FF is equal to mu Fn, right? Which is what we talked about. But if we're specifically talking about kinetic friction, we can say Fk is equal to mu k times Fn, right? We're going to use our kinetic friction coefficient. So we know the normal force. We calculated that already. How can we find the kinetic friction coefficient? Well, we can go to that table. So that table tells us, oh, and what do we have? We have a hockey player glides across ice with steel blades. So let's see if we go down here. Steel on ice. There we go. Kinetic friction or static friction. And in this case, we see we're moving across the ice, so we're going to use that value for kinetic friction. Notice that's a very small value. Only about 1% of the normal force is going to get converted to friction, which makes sense. We know skates, the reason why skates are made of steel is because they glide nicely across the ice, right? So we can calculate it. Fk is equal to 0.01 times our normal force, which is 736 newtons, which, when you calculate it, is going to be 7.36 newtons, or to two significant digits, 7.4 newtons. By the way, do we need to include a unit for the coefficient of friction? I'll let you think about that one. All right, moving on. So we're dragging a 110 kilogram trunk across the floor with a constant velocity. Calculate the coefficient of kinetic friction. So in this case, we don't actually know what the coefficient is, but we can maybe calculate it. So let's start by drawing a free body diagram, which is always a good idea. So we know the trunk is 110 kilograms, so we know 110 times 9.81, we'll assume this is on Earth, 1079 for the force of gravity, and 1079 for the force, the normal force, right? That's Fn, that's Fg, because we know there's no upwards or other upwards or downwards forces, and it's not moving up or down. And the horizontal force, the applied force, is 380 newtons. So it's telling us we're moving the trunk across the floor with a constant velocity. If we just took this object now with this free body diagram, what would that object do? Well, these two forces sort of cancel each other out. This one, 380 newtons, pulling it to the right, so it would accelerate in that direction. But we know that's not the case. There's a constant velocity. So there must be another force to prevent it from accelerating. And we know now that that's the force of friction. And what must the magnitude of that force of friction be? Well, if it's preventing it from accelerating, we know the net force must be 0, so it must be 380 newtons in the opposite direction. Also, is this a kinetic friction or a static friction? Well, it says we're dragging it across the floor, so it's moving. So we'll call this a kinetic friction. So we're asked to find the coefficient of kinetic friction. And we know this relationship, hold on, let me get the blue out. We know this relationship, that the force of kinetic friction is going to be equal to the mu k times the normal force, right? Or in other words, and this equation is actually on your formula sheet, mu k is just equal to the kinetic force or kinetic friction over the normal force. And this is another way to think of mu k. It's the ratio of kinetic force to normal force, right? Or again, the percentage of kinetic force, of the normal force that gets converted into kinetic force. So, kinetic friction, I should say. So we can just plug in our values. The kinetic friction we know is 380 newtons. 380 newtons. And we know the normal force is 1079 newtons. So we can calculate the force of friction, or the coefficient of friction, as 0.352. I'm going to take 3 decimal places because we're going to use this in later parts of this question. 352 newtons, or sorry, not newtons. Because what happens to the units here? The newtons cancel out. And to address the question I asked in the previous question, that kinetic friction coefficient is actually unitless. It's just like a percentage, right? It's just a ratio. So it doesn't actually have a number. If we round to 2 decimal or 2 significant digits, I should say, it's about 0.35. Okay, so about 35% of the normal force gets turned into kinetic friction. Okay, next. A friend decides to help by pulling up on the trunk with a force of 150 newtons. Will this help? So as you're still pushing across the floor with 380 newtons, your friend is sort of lifting it a little bit as you're pushing it. Is this going to make your job easier or harder? Well, we talked about it. Think about it. What's causing the friction force? And we know it's the normal force. The normal force is directly proportional to the friction force. So what happens to the normal force in this case? Well, let's draw a free body diagram. We're going to assume everything else stays the same. So we're going to assume the mass of the box stays the same. So our force of gravity doesn't change at 1079 newtons, right? We know your friend is now pulling up with a force. So we can call this an applied force of 150 newtons, right? We want to know what force we would need to apply in order to pull it at a constant velocity, right? Or a constant speed. So we also know that there is going to be a force of friction acting in this direction, but could be different. We don't know, and we're going to figure that out. Because now we know the coefficient of friction, right? The coefficient of friction is going to stay the same no matter, as long as it's the same two materials sliding over each other. So the question is this free body diagram done? Are we missing any forces? Well, if we look at this the way it is, these two forces, are they canceling out? No, what are we missing? Well, we have a force applied by our friend up at 150 Newton, but we're still going to have a normal force, right? Pulling this box upwards. Or sorry, yeah, supporting this box. Because your friend isn't lifting the whole 1079 newtons. So there must still be a normal force pulling the box up. And in order for that to cancel out with this 1079, we can find that the normal force is just going to be the difference between this and this, right? So if I do 1079, so I'm going to put it over here, Fn equals 1079 minus 150, which is 929 newtons. And that makes sense because we now have these two forces combining to give us to the force of gravity. So this object isn't going to move up or down, but essentially what your friend has done by lifting it up a little bit is reducing that normal force, right, on the object. So in that way, basically the rubbing force of these two surfaces rubbing against each other is going to be less, right, because the normal force is the thing that provides that. So if that's the case, can we calculate our new friction? Because the normal force has changed, the friction changed. So mu k, times Fn, our new Fn. So in this case, mu k, we can assume, because it's the two same materials sliding over each other, that the kinetic friction coefficient stays the same. You'll notice in that table on the other page, it doesn't matter what the normal force is, those always stay the same. So in this case, what was it? 0.352. And then times the normal force, which was 929 newtons. We can calculate this as our kinetic friction times 0.352 is 327 newtons. There we go. So that means the force of kinetic friction has to be 327 newtons. Then what must the force we have to apply to move this thing across the floor be? Well, if it's going to balance out for this so that it doesn't accelerate, it's got to be 327 newtons. So that's our answer essentially. F applied by us has got to be 327 newtons. Okay, there we go. Lastly, our friend sits on top of the trunk. That's not a very nice thing to do because we know it's going to make our job more difficult. Now, what is the new force required to move the box? So similar situation as last one, right? We have the box. We're going to draw a free body diagram. Always draw a free body diagram. We know the force of gravity is 1079 newtons. But now our friend that weighs 55 or has a mass of 55 kilograms sits on top of the box. So they're going to add their mass to that box. So it's like 55 times 9.81. Their force of gravity is going to be another 540 newtons downwards, right? That they're adding from their own mass. So the question is, and of course, we're trying to find this force applied, and we don't know the force of friction, right? Because it's going to change, because potentially the normal force is going to change. So what is that normal force? Well, if we know that this is 1079 newtons down, this is 540 newtons down, the force required to support that mass, or that weight, I should say, is going to be the sum of those two. So in this case, the normal force is going to be 540 plus 1079, which is 540 plus 1079, which is 1619. That is our normal force. So you'll notice the normal force is much higher than it was in the previous question because your friend is just sitting on top of the box, making it more difficult to push. So again, let's calculate. The kinetic friction is just going to be mu k times the normal force. And in this case, mu k, again, we're going to assume 0.352, the normal force of 1619 newtons. So we're going to get times 0.352 is 569.8. So let's round that to two significant figures, 570 newtons. If that's the force that's required, or that's the force that's provided by the friction, the applied force that you're going to need to apply to compensate for that or push it forward at a constant speed is going to also have to be 570 newtons. So that's our answer. Our new F applied has got to be 570 newtons. There we go.